We will discuss a few more problems today. So, we discussed 9 problems in so far. The 10th problem it is given that the molar Helmholtz free energy of a gas is so given that the molar Helmholtz free energy of a gas is AM, is defined as AM, or is expressed as AM equals to minus A by Vm minus RT logarithm of Vm minus B minus Vm naught plus function of temperature, where Vm is the molar volume of the gas, Vm naught is the molar volume of the gas under standard conditions R is the gas constant, A and B empirical constants. And Ft is an arbitrary function of temperature. And we need to find the equation of state for the gas. Okay, the problem says given that the molar Helmholtz free energy of a gas is AM equals to minus A times A by Vm minus RT ln logarithm of Vm minus B by Vm naught plus Ft, where Vm is the molar volume of the gas and Vm naught is the molar volume of the gas under standard conditions. R is the gas constant, A and B are empirical constants, and Ft is an arbitrary function of temperature. We need to find the equation of state for the gas. Okay. Now, we know how to solve this one. So, basically we need to calculate P has to be related to the volume in order to obtain or in order to get the equation of state of the gas. Okay. So, how do we solve this? We have AM is minus A by Vm minus RT Vm minus B by Vm naught plus function of temperature. We know dA is minus PdV minus SdT. So, del A by del V at constant temperature gives us P. So, we can write del AM by del Vm at constant temperature gives us pressure. So, this is our equation 1 suppose. So, we need to differentiate AM with respect to Vm at constant temperature. If we do it, we get A by Vm to the 2 minus RT Vm minus B, and this is our equation 2. So, we write P is minus A by Vm to the 2 minus plus RT by Vm minus B, or we get P plus A by Vm to the 2 times Vm minus B is RT. So, this is the gas equation of state. Very simple problem. Next, we will discuss another problem. Problem number 11. At 1 atmospheric pressure, one mole of steam is condensed at 100 degrees Celsius. The water that we get after condensation is cooled to 0 degrees Celsius and then frozen to ice. What is the value of total entropy change delta S for this process? So, the problem states at 1 atmospheric pressure 1 mole of steam is condensed at 100 degrees Celsius. The water is cooled to 0 degrees Celsius and then frozen to ice. What is the value of total entropy change for this process? Given the heat of vaporization and fusion are are 540 calorie gram and 80 calorie 540 calorie per gram and 80 calorie per gram respectively. And the average heat capacity of liquid water is 1 calorie per gram per degree. Okay, the problem says at 1 atmospheric pressure 1 mole of steam is condensed at 100 degrees Celsius. The water is cooled to 0 degrees Celsius and then frozen to ice. What is the value of total entropy change for this process? Given the heat of vaporization and fusion are 540 calorie per gram and 80 calorie per gram respectively, and the average heat capacity of liquid water is 1 calorie per gram per degree. Now, how to solve? So, basically total entropy change for this process is entropy change. So, we have first steam which is condensed water. So, delta S vapor to liquid plus delta S liquid at temperature at 0° centigrade to 100° centigrade. So, liquid to liquid rather, and then delta S is equal to solid. So, we need to calculate 3 different entropy change for 3 different processes separately, and then if we add them up we get total entropy change for the whole process. Okay. So, we have 1 mole of water. So, 1 mole of water means everything is expressed here in terms of per gram. So, 1 mole of water is equals to 18 gram. Okay. So, delta S vapor to liquid for this condensation process. So, vapor to liquid. So, heat is released by the system. So, we have the minus sign here. So, 18 times 540 by temperature is 373. Okay. And it gives us minus 26.06 calorie per Kelvin. And delta S liquid to liquid, okay, for this we use the relation mCp T2 by T1 is 18 times 1 times 1 ln 273 by 373, and it gives us minus 5.62 calorie per Kelvin. And delta A is liquid to solid, again heat is released here. So, we have the minus sign here and we get minus 18 times 80 divided by 273, and it gives us minus 5.27 calorie per Kelvin. So, delta S total is minus 26.06 minus 5.62 minus 5.27 calorie per Kelvin, and it gives us minus 36.95 calorie per Kelvin. This is we need to carry out, we need to understand the problem here, and we get total entropy change negative. So, entropy decreases, which is expected because we started with steam and we find and our final state is ice. Okay, so, from vapor we are going to the solid state. So, entropy change has to be negative here. Okay. Next problem we discuss a system undergoes a certain change in state by path 1 and the corresponding heat absorbed and work done by the system are ten calorie and 0 calorie respectively. for the same change in state by another path, path 2, the above respective quantities are 15 calorie and 0.5 times W max, where W max represents the work if the specified change is reversibly carried out. What is the value of W max? So, this problem states a system undergoes a certain change in state by path 1 and the corresponding heat absorbed and the work done by the system are 10 calorie and 0 calorie respectively. For the same change in state by path 2, the above respective quantities are 15 calorie and 0.5 W max, where W max represents the work if the specified change is reversibly carried out. What is the value of W max? So, basically here we are starting from the same initial state and we are going to the same final state where two different paths. One is path 1 and another is path 2, and we get different amount of heat absorbed and work done for two different paths, because work and heat both are path functions. Whereas internal energy change is a state function. So, the internal energy change for the both the processes are the same. Okay. So, what I said is, so we have the same initial state and we have the same final state. This is our path 1. So, this is our initial state and we are going to the same final state in two different paths. So, this is our path 2. Since internal energy is a state function, we can write 10 plus 0 calorie equals to 15 calorie plus 0.5 max. So, if we solve this, we get, so here work done by the system. So, this is negative here and this is also negative here, because work done by the system. So, we get 0.5 times W max is 5 calorie, or we get W max equals to 10 calorie. So, two things you need to know here. One is internal energy is a state function and you have to read the question carefully, like here heat absorbed. So, heat absorbed means Q is positive here and work done by the system. So, W is negative here according to the convention we follow. And if we equate them, since internal energy change is the same for path 1 and path 2. So, we can equate this 10 minus 0 calorie equals to 15 calorie minus 0.5 times W max, and we get the value of W max, which is equals to 10 calorie. Next problem, problem number 13. In the vaporization of benzene at 1 atmospheric pressure or at 1 bar pressure, delta H is 7364 calorie and delta S is 20.85 calorie. What is the normal boiling point of benzene? So, this problem says the heat of vaporization of benzene at 1 bar pressure is delta H is 7364 calorie and delta S is 28.85 calorie. What is the normal boiling point of benzene? So, vaporization process is an equilibrium process. So, vaporization process is an equilibrium process, and during vaporization there is no change in the temperature. So, delta G T P is 0. So, it says delta H is T delta S. So, T here is the transition temperature, which is nothing but the boiling point of normal boiling point of benzene. Normal means we are considering 1 bar pressure here. So, T transition is delta H by delta S, and we get 7364 by, this is 28 calorie per Kelvin. Okay, so 20.85 Kelvin, and we get the value of, and the value is 353.19 Kelvin. So, this is the answer. Next, we consider one analytical problem. 2 moles of an ideal monatomic gas, Cb is 3R by 2, is mixed with 3 moles of an ideal diatomic gas, for which Cb is 5R by 2 at room temperature. Calculate Cp mix for the mixer. A very simple problem. It says 2 moles of an ideal monatomic gas, for which Cv is 3R by 2, is mixed with 3 moles of an ideal diatomic gas, where Cv is, for which Cv is 5R by 2 at room temperature. You have to calculate Cp max for the mixer. So, here problem how to solve it. Okay, it's extremely easy problem. So, total internal energy is U1 plus U2. So, we can write del U by del T at constant volume is del U1 by del T at constant volume plus del U2 by del T at constant volume. So, 1 represents ideal monatomic gas and 2 represents diatomic gas here. So, in CV mix is N1 CV1 plus N2 CV2. So, total number of moles N is total number of moles N is 2 plus 3 equals to 5. So, 5 times CV mix is 2 times 3R by 2 plus 3 times 5R by 2. So, we get CV mix 21 R by 10. Okay. And so, CP mix, we need to calculate CP mix. CP mix, we have got CP mix is CP mix is R plus CP mix. So, we get R plus 21 R by 10. So, we get 31 R by 10. It's extremely easy problem. We will solve another interesting problem, but conceptual problem. Again, this is an analytical problem. 2 moles of an ideal monatomic gas undergoes a cyclic process A, B, C, A as shown in the figure below. So, the problem says 2 moles of an ideal monatomic gas undergoes a cyclic process ABCA as shown in the figure below. And what we need to do? We need to calculate the ratio of temperature at B and A. So, here you can see that at point A, both pressure at point A and C, both pressure and volume are given, whereas at point B only pressure is given, volume is not given. So, we need to calculate first what is the volume at point B. Okay. So, how do we do that? Okay. So, basically what we do here, we draw in the solution, what we do is we So, what we do here, we draw one perpendicular line starting from B, which meets at point D on line AC. Okay. Now, what are given here? So, n number of moles n is 2 here. At point A, if we say temperature is TA, is P naught V naught by 2 times R, right. At point B, pressure is 3 P naught, volume at point B is not known. Now, we can write AD is nothing but BD cot of 60 degree, right. So, we get AD by DC is 1 by 3, okay, because, and we can write AD is this and DC is BD cot 30 degree. So, if we take the ratio of these two, we get 1 by 3, or we can write AD 3 AD is DC. Okay, now, what is AC? So, AC is AD plus DC, and value of AC is 6 V naught minus V naught, nothing but 5 V naught, and AD and DC is 3 AD, so it gives 4 AD. So, AD is 5 by 4 times V naught. So, volume at point D point B or D, whatever you say, is V naught plus 5 by 4 V naught gives you 9 by 5 V naught. Okay, so, we get volume at point B, that is nothing but VB, we say, is 9 by 5 V naught. So, we get, we know PV is N at T. So, P at pressure B times V at pressure B is 2 times R TB. So, TB is P times PV times VV by 2R. PB is 3 P naught, VB is 9 by 5 times V naught by 2R. So, we get 27 P naught V naught by 10R. So, this is the value of TB, and what is the value of TA? And TA we have pressure at temperature at point A is P naught V naught by T 2R, P naught V naught by 2R. So, the ratio of temperatures at B and A TB by TA gives us 27 by 10 times 2, so it gives 27 by 5. Okay, so this is the TB is to TA is 27 is to 5. So, this is problem 15, and we will discuss one more problem 16. Problem number 16 is helium of mass 1.6 gram is expanded adiabatically 3 times and then compressed isothermally to the initial volume. Find delta S for the process. So, this problem says helium of mass 16 gram is expanded adiabatically 3 times and then compressed isothermally to the initial volume, and you need to calculate entropy change for this process. Now, for the first process, this adiabatic process, so Q is 0. For adiabatic process, Q is 0. So, delta S1 is 0. Okay. Now, total entropy change for the process, total entropy change delta S is delta S1 plus delta S2, and delta S1 is 0 and delta S2 is n Cp ln T2 by T1, and the gas is, what is n? N is 1.6 gram by 4, so this is 0.4, right? It's because we are considering helium here, and Cp, helium is monoatomic, so Cp is 5 R by 2, or we can write 5 R by 2 here, and then we can write delta S2 is 0.4 times 5 R by 2 ln T2 by T1. So, now process is isothermal one. So, T2 by T1, this is not isothermally, this is isobarically process, compressed isobarically, do not consider isothermally, isobarically here. So, for isobaric process, pressure is constant, so T2 by T1 is V2 by V1, okay, and this gives you 1 by 3. So, delta S2 is giving us like minus 2.2 calorie per Kelvin. Okay. So, the problem is little bit modified now. Helium of mass 1.6 gram is expanded adiabatically 3 times and then compressed isobarically. The process is isobaric one, isobarically to the initial volume. find the delta S for the process. So, isobaric process means pressure is constant say A here, so T2 by T1 is nothing but V2 by V1 and volume is decreased to 1/3 of initial volume. So, we get 1 by 3 here. And if we substitute all these things, we get delta S2 is this, delta S2 is minus 2.2 calorie. So, delta S2 is nothing but minus 2.2 calorie per Kelvin. Thank you.